Hey, welcome to NASA Edge.
An inside and outside look
at all things NASA.
Oh, that's going to leave a mark. Welcome to NASA Edge.
An inside and outside look
at all things NASA.
And we're going to be talking about the future of aeronautics today.
Yes, a very exciting topic.
And in fact, NASA does a lot of aeronautics research at 4 field centers across the country.
Sure do.
We're here at NASA Langley Research Center. Mm-hmm. Where are the other 3, Franklin?
Glenn Research Center.
In Ohio.
Ames.
California.
And Dryden.
Dryden Flight Research Center, also in California.
And interestingly, we have to use flight to get to those centers when we visit.
That's true. And in fact, we travel quite a bit on the show. We go from field center to field center, covering the very cool topics from exploration to science to aeronautics now. So you know how it is in airports. Sometimes our planes are delayed.
Bedlam.
We're on the tarmac sometimes for an extended period of time. The noise level on the planes are pretty loud. I mean, sometimes it can get, kind of frustrating.
Yeah, it's really interesting to think that actually NASA is tackling those issues,
right,
trying to improve the quality of life for travelers all across the country, and in fact the world.
And then the challenge is going to be, instead of just tackling those issues individually, how can you tackle that all at one time so that you can develop an aircraft that is quiet, that's efficient, rated better for safety, and also cost effective.
And they're nicknaming this green aviation as they're trying to tackle all these approaches.
Do you think, Franklin, that NASA may have bitten off more than they can chew in this lofty endeavor? Because that's actually doing a lot of stuff.
But we have a lot of bright people here at NASA, especially here at NASA Langley, where we actually have a chance to talk to 2 engineers. And the first interview that we're going to look at is from Karen Taminger, who's an engineer. And we actually had a chance to talk with her in the TDT. TDT, not TNT.
In fact, you startled me because I was like, I didn't know it was a show on explosives. So.
It's a very famous wind tunnel here at NASA Langley, and TDT stands for, Franklin?
The Transonic Dynamics Tunnel.
And if you want to learn more about this historical wind tunnel, just go to nasa.gov, look up TDT in the search engine, and you'll find a ton of info about the tunnel.
I can't do that now, but I'm still confused by transonic. What exactly does that mean?
Well, let's go to Karen Taminger's piece, and when we come back, we'll explain what transonic means.
Great.
Right, let's check out the interview. Hey, we're here in the historic TDT tunnel with Karen Taminger. And Karen, what do you do here at NASA Langley?
I'm the Associate Principal Investigator for Subsonic Fixed Wing Project, specifically looking at structures, aeroelasticity, and materials.
That's a mouthful.
It is a mouthful. I like to tell the people in my program that I am SAM.
SAM, structures, aeroelasticity, and materials. That's
exactly.
Awesome. So Karen, what's the future of aeronautics going to look like?
Airplanes in the future may look very similar to airplanes today from the outside, but we're making the changes on the inside, trying to make them more efficient. We're improving the engine so that they burn less fossil fuels or no fossil fuels. We're also looking at trying to improve the structures on the inside of the airplane so that the airplane is far more resilient and more responsive to the environment. One of the improvements we're trying to make in an attempt to reduce the weight and also reduce the manufacturing time and cost to assemble aircraft is to eliminate rivets and to improve the assembly. And so we've got, both in metals and in composite structures, we've got new technologies that are being developed on the material side that enable you to build entire structures or large parts of structures, and then you can assemble large components rather than trying to assemble them at a very small level. This is demonstrating a variety of concepts that have all come together into a single component. What we see is a single piece skin with stiffeners on it, but instead of stiffeners being straight and riveted, they're all built into the structure.
Oh, wow. Now, this is just a piece of aluminum.
This is a piece of aluminum. Some of the new manufacturing technologies enable us to build not only the stiffeners integral to the skin, but also enable us to build them at varying heights and shapes. The curvature allows us to eliminate some of the crack propagation routes in a traditional structure.
So in other words, it's essentially that aircraft could be essentially much stronger.
It could be stronger. The other thing that we're trying to do is eliminate the noise transmission from the aerodynamics on the outside of the airplane getting into the fuselage. And what we found is that by changing the stiffener's location and shape, we can actually eliminate the resonance of this particular panel so that the acoustics don't get in the first place.
So Karen, this is something similar to the piece of aluminum, but this is a composite material?
Yes, this is a composite structure called Perseus, which stands for Pultruded Rod Stitched Efficient Unitized Structure. It's got several features in it that's an improvement over traditional composite structures in that it's stitched together, which helps improve the load transfer from the skin into the stiffeners. It also helps to improve the damage tolerance because it doesn't allow cracks to propagate through the structure as efficiently. This outside part would be the skin of the aircraft, and then these are the stiffeners and the ring frames that are carrying all of the load inside of the fuselage. This could also be used in wing panels where it would provide stiffness for the wings.
There's potentially the fuselage of the aircraft could just be in big sections as opposed to smaller sections that they build now?
Yes, the 787 is groundbreaking in that respect because the 787 is built very large sections out of composites all in single piece, and then it's got just a few components that need to be assembled.
Now the 787, that's the Dreamliner, which is going to be Boeing's new aircraft for the future?
Yes, exactly.
And that should be, and that's already flown, right?
It's had some of its maiden flights, and it's going through testing and FAA certification right now.
Speaking of a cool aircraft, we have a nice one right behind us. What kind of model is this?
This model is specifically looking at aerodynamic efficiency improvements, trying to improve the way aircraft fly. Future aircraft may have longer high aspect ratio wings in order to capitalize on low drag, improved laminar flow, just as the wings you see on this aircraft. Because of those long high aspect ratio wings, they tend to have problems with flutter, which is one of the things that we test here in the TDT.
Okay.
And so flutter is an unsteady oscillation that occurs either from an unsteadiness in the airflow or just from the interactions of the structure with the air as it moves through. One of the things that this model is looking at is, can we stiffen those wings externally by bracing them with the struts that are going from the tail to the tips of the wings. And the real benefit in looking at changing the external surface is trying to get to 70% reduction in fuel burn and 70% reduction in the acoustics and the emissions that are currently emitted on flying aircraft today. And so in order to get that drastic a level of reduction, sometimes we need to try some things that are new and different. They also have impacts on current aircraft. From the inside out, we can implement these things. But ultimately, future aircraft may look very different from today.
That's good. Well, Karen, thank you so much. We look forward to the future of aeronautics, and hopefully one day we'll be able to fly something like this in the future.
Thank you.
Wow, that was an impressive aircraft. What was that?
Yeah, it's called the Joined Wing Wind Tunnel Model.
I was kind of hoping for a cooler name like Falcon or something.
Well, it's it's just a test model right now. I mean, they're looking at high altitude, high endurance unmanned aircraft.
Interesting. Franklin, one thing I noticed about this test was all the emphasis on materials.
And that's one of the things that they test in the transonic dynamics tunnel is materials and whether or not they're steady or unsteady.
Yeah, because I always thought it was engine design and things like that. I didn't realize that so much went into actually what it was made of.
Well, if you can make a rivetless aircraft and save a ton of weight, I mean, it's going to save on fuel costs, save on money.
Yes, we here at NASA Edge are anti-rivet. So, right. but you owe me one definition real quickly, if you don't mind. What's the definition of transonic? I wasn't quite sure about that.
Okay, well, we know subsonic is traveling less than the speed of sound. Supersonic is traveling faster than the speed of sound. And then we have hypersonic, is traveling much, much faster, 4,000 miles an hour faster. But transonic is looking at speeds near the speed of sound.
Okay, so that's very important then if you're testing aircraft of this kind. You want to be able to approach the speed of sound.
Yeah, well, NASA is testing aircraft at all flight regimes, from subsonic all the way to hypersonic.
Ah, very cool.
Hey guys, let's take a break, and when we come back, we'll talk about green aviation and what NASA's doing to reduce flight noise.
Green aviation?
Is that why you wore the green shirt?
Green shirt. Yep, you got it.
Hey, welcome back, and we're here to talk about a very cool segment of the show on green aviation.
And Franklin's wearing his very colossal green shirt in honor of that.
Absolutely. So, NASA has some pretty lofty goals when it comes to green aviation.
Lofty, nice.
And so what they want to do is they want to reduce aircraft fuel consumption, emissions, and noise simultaneously, which is a much more difficult challenge if you just try to tackle each individual one first. So, if you look at it, fuel efficiency, emissions, and noise. Tough challenge.
Yeah, and in fact, Franklin, I don't know about you, but I don't really think about noise in terms of being a green issue at all.
Well, noise is pollution, and around
point.
the airports, that has been a number one concern of the residents, is that the air pollution and the noise pollution that come from aircraft has been too high.
Well, if you look at each of these factors real quick, fuel efficiency. Do you realize in 2008, U.S. commercial air carriers burned 19.7 billion gallons of jet fuel, while aircraft owned and operated by DoD burned another 4.6 billion gallons of jet fuel?
Wow, that's amazing.
At $3 per gallon, that's a cost of $73 billion in fuel.
Man, who's paying $3 a gallon?
Well, back in 2000.
Oh, yeah. Okay. All right. Fair enough.
And if you look at emissions as well, we're trying to reduce emissions by 20% by 2015, 50% by 2020, and greater than 50% by 2025. And noise, it says the aircraft noise continues to be regarded as the most significant hindrance to increasing the capacity of the national airspace system.
And also, as a fashion statement, it's really tricky on those guys out on the tarmac to have to wear those big earphones. I mean, hard to look cool out there directing traffic when you got those things going on, but they're necessary. Don't get me wrong. That's safety, and that's important.
Well, tell us about the interview.
I talked to Florence Hutchison, who's an engineer. She works in the QFF, or the Quiet Flow Facility, and she talked to me briefly about what NASA is doing to reduce aircraft noise. Let's take a look at that interview.
Cool.
Hey guys, we're here with Florence here at the QFF, or the Quiet Flow Facility at the NASA Langley Research Center.
Yes.
We're talking about green aviation.
Yes.
What is green aviation?
Green aviation is about aircraft that have minimum impact on the environment. So NASA is working on meeting the goals of green aviation. Some of the impacts we're concerned with are noise, fuel burns, and emissions. We don't want to pollute the air. Presently, NASA is working with the FAA to develop the next generation of air traffic control to improve airport capacity and to minimize delays in the air and on the ground. These are one of the close partnership and projects that they're working on together. But one I'm personally involved with is a hybrid wing body project that will be drastically quieter than current aircraft.
This configuration is similar to that of the blended wing body of years past?
Yes, it is very similar, with the main exceptions that in the blended wing bodies that we have seen out there is the engines. There's three-bodied engines that are overhanging in the back of the aircraft. Whereas for this hybrid wing body concept, we're looking at two engines that are located much further forward, so we can get some shielding of the noise sources in the back of the engine, which is a challenge because those noise sources are really distributed in nature, so it makes it harder to shield them.
I take it here in the Quiet Flow Facility, you are trying to lighten the amount of noise that's coming from the aircraft body.
We concentrate on the noise goal. We developing quieter aircraft. So this facility is specifically designed for aeroacoustic testing, where aeroacoustics is the science of aerodynamically generated sound. So we look at how it is generated, how it radiates, how it propagates, how it interacts with other obstacles, different techniques to measure it and also to predict it. So the facility is specifically designed for anechoic testing. You see all these wedges around us, and those are there to absorb the sound that is coming from the test section, because we do not want any sound wave to be reflected off the walls, because they will interfere with the noise that we are trying to measure, the noise that is directly radiating from our test model.
Are the articles or the pieces of the aircraft that you put in this test section, are they full scale or scaled down?
They are scaled down. Yeah, we usually look at just aircraft components, like a landing gear or a section of the wing with a flap or with a slat. And they're usually about 6% scale. So we're looking at scaled model. We put our model in this test section where you can see the exit plane of the nozzle. The air is coming from the nozzle, going up between those two side plates and exit through this collector in the ceiling. As the air is flowing around that aircraft component, it is generating noise. So we use microphones to measure that noise, and more specifically, we use an array of microphones that you can see here located on this boom. So it's a cluster of 41 microphones for this one specifically. And this area of microphone is used to really pinpoint at different locations around your test model, so we can determine exactly where the noise is coming from and also quantify its strength for each different location on the test model.
What are your goals as far as reducing the noise?
Yes. So for Griva Aviation right now, our goals are to confine the objectionable noise to within the airport boundaries. This means reducing the noise from every aircraft in the fleet, from the small commuter planes with propellers to the large commercial airliners. NASA and its partners hope to reduce future aircraft noise profiles by about 83% as compared to current levels. Also, we hope to reduce future aircraft emissions by 75% and fuel consumptions by about 50% as compared to current levels. A greener future for aviation holds the promise of new life for airports, because people will be able to enjoy the convenience and commercial benefits of living near an airport without enduring the racket and fumes that are so aggravating today.
Well, that's good. That's good to hear. Well, Florence,
Oui.
thank you so very much for talking to us today.
You're very welcome.
And here at the Quiet Flow facility at the NASA Langley Research Center.
Thank you.
It's nice. Can I get some of these for my house?
Sure, you can take a few. We actually have some extra ones.
Good interview with Dr. Hutchison. She gave me a list of places to visit in France when I go back.
Well, we need to plan that trip because
Bonjour, ça va?
yeah, very nice interview. And she's great. She's very easy to work with.
Oui.
But the cool thing, going back to green aviation, going back to his shirt color, some of the solutions that NASA's working on, that Florence is working on, or Karen's working on, we want to improve aircraft design by looking at lightweight structures, composite materials, changes in engine design, making them more efficient. Looking at the whole air transportation system. We talked about that next generation transportation system by 2025. So there's a lot of different factors that go into green aviation, and it's a huge field.
Yeah, in fact, I was surprised in the interview that how much attention was given to things like landing gear. And it's like you drop the landing gear, it's like blowing a whistle or something. Here we are, we're going to land.
Absolutely. And she talked about, when aircraft are coming into the airport, they're moving a lot slower. And when the landing gear comes out, it's just another obstruction in the flow of the air around the aircraft, which causes so much noise. So that's what they're working on to reduce the noise in the QFF.
That's good stuff, Franklin. But we got to take a break.
Absolutely. When we come back, you'll find out what new development has Langley all abuzz. You're watching NASA Edge. Welcome back to NASA Edge.
I can see we have interesting spread here.
Yeah, well, see, the buzz, Franklin, as you know, as we all know, you're now a new father.
That's true. I am a new father. Baby boy,
yes.
Adam Christopher, was born on July 13th. And I go use the restroom between the breaks. I come back and I see this.
That's right. And Ron, do we have a picture of the baby we can put up?
There it is.
The baby. Picture of the baby?
There's another one.
Okay, Adam.
Oh, here you go.
Oh, there we go. Yeah. Sorry, man.
Who's that?
It's Adam.
That's not Adam.
Well, yeah, that. Really? Anyway, before we move on, we do want to get back to aeronautics.
Yes.
But I did want to say, on behalf of the entire NASA Edge crew, congratulations. And as a special kind of offering, I just want to let you know, in all seriousness, I offer my services as Adam's godfather and instruct him in the ways of the world if necessary. And Franklin, I believe.
I'm Uncle Franklin.
Well, be careful when you say godfather, because
Right.
if you're going to pay for the child's education, I'm all for it then. Penn State, out-of-state tuition, not a problem.
Pseudo godfather, god brother, maybe, if such a thing exists.
Hey, I got 5 on it.
But speaking of education, we
Yes.
have a cool segment coming up here.
We do.
We do have, there's a lot of engineers here at NASA Langley who mentor kids. We bring in a lot of students from university levels and even high school. One engineer, Gary Qualls, was fortunate enough to bring in 10 students this summer to work on a very cool project.
Yeah.
Tell a little bit more about that.
Well, actually, what they're doing is sort of an accident avoidance system for these remote helicopters.
Right.
So they actually do collision avoidance and things like that using really interesting technology.
Right.
And one of the students happens to be Amanda, who has been a field reporter for us.
That's right. That's right.
So let's take a look at the clip. Yes, we're here with Gary Qualls, and I understand you worked with a bunch of students this summer. What actually did you guys work on?
Well, we've had a group of 10 students working on a small robotics lab. We've got a combination of ground vehicles and some aerial vehicles. We've got a blimp. Mostly we've been focusing on some quad-rotor helicopters, which are small helicopters with 4 motors that keep them up. And the students have been teaching them how to fly around in a volume and interact with each other. And that's the whole idea of the lab, is to find out how these kind of interactions will work best. And they are situations that could vary from small planes in real airspace to robots flying around indoors. So to get this kind of work done, the students have had to look at computer programming. These kind of robots have code on board that's controlling how they work. We use a lot of open source software for that. All the robots are talking to ground computers that have software running on them that the students have written. Most of the 10 students at this point have written their own control programs from scratch to control different vehicles, either ground vehicles, simulated airplanes flying around the county, and also these quadrotors flying around inside the lab. We've got electrical engineering students, computer science students, we've got psychology students, aerospace engineering students, mechanical engineering students, and they're all having to work across several different disciplines. They're all writing code, they're all checking electronics, they're all soldering stuff together, finding out what doesn't work. Because solving these kind of problems is different from the normal kind of problems you get in a lab at school. In a lab or a homework assignment, you're given everything you need to be able to solve the problem. And those are not the kind of problems that you get out in the real world, and it's not the kind of problems we're giving them here in the lab. We're giving them problems where they have to do a lot of research online or go to the library, start conversations with people who are writing the open source software they're trying to use. Those people will change the software to help us out and do our job. So it's a very interactive, very cross-discipline project. To see them, toward the end of the summer, kind of come into their own and feel very comfortable with electronics, very comfortable with software they've written, and be able to work together as a good team. I mean, it's a really good feeling to see everything come together.
We got to get one of those quadcopters for this office here.
And for Adam, he could airlift in new diapers. You can have him bring them to you, and you can hold your hands up, and the helicopter drop the gloves on, and you're good to go.
There you go.
For the record, he uses gloves to change diapers.
Hey, before we go, we have to wrap up the show because we're running short on time. I do want to mention one important thing. We talked about education.
Mm-hmm. Yeah.
If you're a student out there, if you're a high school, if you're a college student, Aeronautics has a lot of cool programs that you can participate in. If you just go to aeronautics.nasa.gov/education, you can go to that website and see a list of competitions, education programs. If you're teachers, you can download cool activities. I really encourage you to go to that website.
And if you're a really sharp student, then you'll end up doing things like Amanda with Gary Qualls, or if you're a really poor student, you'll end up here in the NASA Edge studios on diaper duty.
And for the record, I don't use the gloves anymore, so that was old.
Yes, that's great. That's good news. You're growing.
You're watching NASA Edge.
An inside-outside look at all things NASA.
He's becoming more fatherly.
I still can't believe you're wearing diapers.